Morning. This is lesson 16, so lecture type lesson. So we are going to learn tolerancing system and geometric tolerancing symbols. Okay, so the tolerancing is a total amount of specific dimension is permitted to vary. Okay, so it's a description of the tolerance. Uh, in the mass production, when we produce the product in very big amount, we call mass production. Okay, so the production rate is very big. So in one day, for example, a car or any good, any product can be produced many times. Every day we're producing thousands of cars, so that calls a mass production. And for that car, we're fabricating many parts. The parts also we need every single parts are thousand times everyone, and then every part, and then we are assembling. Finally we will assemble all of those parts every day. So that calls mass production. Okay, so in mass production, all parts should fit together properly, otherwise you cannot assemble correctly. So that's why and also every parts are might be produced with some error, so those errors should be counted. Okay, so those errors should be taken into account. So we have to care about those errors also. Okay, so for that purpose, we'll have kind of a tolerance system. Okay, so later in after this slide, so I will show you what's a tolerance system and why how we solve those problems. Okay, so the problem in the mass production. Okay, so to solve those things, we need a tolerance. Okay, so the definition of the tolerance is, okay, so geometric tolerance. When we say the tolerance in this lecture, we mean geometric tolerance. Okay, so there is a different tolerances also, but we are talking about geometric tolerance. Okay, so tolerance is a total amount of specific dimension. Specific dimension is permitted to vary. Okay, so that is taken from ANSI and ASME, American Standard Mechanical Engineers, American Society of Mechanical Engineers. From that one, we got that definition. And if you say what's the meaning of this? For example, there is a cylinder is given. Okay, so the front view here, and that is a cross section. Okay, so left view from here, the left hand side view. So this is okay. So left view, and the diameter of this cylinder. So if you see here, diameter sign, and then 16.25, and that has kind of a tolerance value, like okay, so the upper level is 16.25 plus the biggest one, in B case 0.02. So if you sum these two values, you will get 16.27. And if you subtract this value, 16.25 minus 0.02, you will get 16.23. Then the values from 16.23, there is 16.24, 25, 26, and the final one 27, right? So there is several values inside of this one. Okay, so in between 23 up to 27, there are many values could be. Okay, so many values. 16.235, 16.2357, 16.24, 16.245. So a lot of the values might be inside of this. All are allowed. The meaning of this tolerance is all these values, if you produce the part with this diameter, all are allowed. If you get the size 16.28, that is not allowed because that is out of this tolerance. Okay, so the allowed, the biggest should be 27. More than this is not allowed, or less than this is not allowed. Okay, so if you get 16.22, it's not allowed. Okay, so everything allowed within this region, within this tolerance. Okay, so within this inside of 23 and 27, all are allowed. Okay, so those amount. Okay, so amount of permitted to vary, the values are giving us the geometric tolerance. So biggest possible part is 16.27, and smallest possible is 16.23. So in between also allowed to assemble. Okay, so in the morning the worker might produce the part with size 16.23, and in the midday he might produce 16.25, and at the end of the working day he might produce 16.27. All are correct. If he get the size, okay, so dimension 16 point out of the tolerance 16.29, he have to change it, okay, repair it. He have to make some another operation to reduce this size until 27 or smaller than this value. So it should be inside of this. Okay, so and if you set only 16 0, like without tolerance, so you cannot produce this one. So how you get this 0? If you see this one under the microscope, you will see some values there. Okay, so it means, so you need to give kind of a region. Okay, so tolerance region. So the outer tolerance. Okay, so bigger value and smaller value. So then you are allowing it's inside of these values. So then you will select based on this, you will select a measurement. Okay, so a measuring device, and based on this you will select a the machine. Okay, so manufacturing tool or machine. So and then you are producing, and then you're checking with your measurement. So if this one is inside of this, you're accepting it, and then you're assemble all those inside of these things. What's outside of this, you have to repair it. Okay, so or recycle it. Okay, until you get this value in what's inside. Okay, so that's the meaning of the tolerance. Otherwise you cannot produce. Otherwise your production price will rise up and your product will be very expensive. So no one cannot afford it. No one cannot buy it. Okay, so to reduce, in order to reduce the price of the product, so we're making kind of tolerances. Okay, so if you give wider tolerance, so price will be cheaper, but the quality will be getting worse. If you make very narrow tolerance, so the product price will be very expensive, but the quality might be good, but no one cannot afford it. No one cannot buy it. Okay, so that's a key. So if you see the cylindric shapes,
So there is a variations in the form. If you see closely under the microscope, so there is a variation. It's the errors. Okay, so various imperfections is not perfect in reality. If you see the parts, you will see the imperfections, not perfect places. Okay, so various imperfections of the form may occur in manufacturing cylinders. Okay, so it might be one of this. So part is wasted if you cut in the middle more than the tips, two ends, so it is more, there is a distance. Okay, so it's rotating when you're cutting. So we call this part is wasted. So it should be like this, but you're wasting like this. Okay, so this area is wasted. And this one is part is tapered. So it should be straight like this, but you're pressing more here, so then you get like this taper shape. And part is bowed, so in the middle part is bended, kind of, you know, it's become like this bended part. Okay, so in this area is bended, and so we call part is bowed. And part is barreled, kind of barrel. So we are making more force here, so we are losing the force for cutting. Then it become like this bowl shape. So the part in reality might have several this kind of errors when you are producing. So to understand it, how to set your requirement. So we are requiring, so tolerance is requirement, like, okay, so the upper level should be this, and lower one is with -1. Okay, so upper region required. Okay, so allowed region and lower allowed region, kind of, you know. So here we see upper boundary and lower boundary. So we need to, it's required to manufacture the part inside of these boundaries. So this is upper boundary, and that is lower boundary. Okay, so it's a radio. Okay, it's kind of a diameter. Okay, so and the part should be inside of this allowed. So if you, so this is a part. Okay, so we need to be under the upper boundary. So then in case of this is okay. And also we have to check the lower boundary also. And if your part is smaller than the lower boundary, so this is lower boundary and that is upper boundary. So here you can see the part is, this is a part. Part has become more smaller than lower boundary, so that's not good, please. And also in here the parts is exceeded. Okay, so become a bigger than upper boundary, so that's also not good places, but you can repair it. Okay, so you can repair it in next operation, but in case of this you cannot repair, so you have to recycle it. We cannot accept this one. Okay, but in case of this so it's exceeded from the upper boundary. Okay, so this is upper boundary, and part become a more bigger in upper boundary than upper boundary, so we cannot, we can cut it in the next operation. Okay, so that's okay, so we can repair it, and then check it again if it's okay, so you can accept it. So that's a way of tolerance. Okay. And why we need a tolerance? If you have just single part, and if you have no any assembly operation, so you don't need a tolerance. How you produce, which in which size, so you can you can use it. But if you have many parts, you have to fit them, okay, with each other. So then you need to check it. So okay, so for example, if you have part with, okay, so 12.47, so another part is 12.51, so you have to add it. Okay, so your part should go inside this hole, so you have to check the sizes. If not, so your manufacturing process will vary based on this. So that's why there is a types of the mating parts. Okay, so tolerances. So the fits between mating parts. Okay, so this is a, we call this one is a shaft, and this is a part with hole. Okay, we are assembling we are many times we are assembling shaft and hole, part with shaft and part with holes. And so all of them, the shafts also have own tolerances, so it might be bigger one and smaller one and in between one. And holes also has the tolerance levels, right? The smaller one, smaller boundary and upper boundary. Okay, so and in between the dimensions. So based on these things, based on this dimension, okay, the tolerances, it varies. Okay, so 3 types. The first type is clearance fit, second is interference fit, and transition fit. What's the difference? And let's see the different okay, the definition of fit. Fit is the range of tightness or looseness. Okay, so if you insert this one inside of the hole, so there will be some value of, okay, so empty room. So level of that empty place, the area, if that one is more tighter or more emptier, or we call looseness. Okay, so the fit will different. Okay, so resulting from the allowance and tolerances in mating parts. Okay, the difference between the largest allowable shaft size and the smallest allowable hole size is called the allowance. Okay, so let's see the first one. Okay, so clearance fit, so this one. So we call clearance fit when the shaft, okay, so this is a shaft, has smaller sizes than the hole. Okay, so every time shaft has a smaller size, like okay, so the upper one is 47, okay, 12.47, and smallest possible is, okay, 12.47, and biggest one is 48, and in between it can be 12.47, 5, 6, 7. Okay, so and finally 48. All these values can insert it into the whole part, the whole located part, but still there will be at place. Okay, so so you see the smallest possible hole is 12.50, and biggest is more than this, bigger than this even though. Okay, 12.51. And here if you see the biggest possible shaft, if you insert the biggest shaft inside this hole, is smaller than the smallest hole even though. Okay, so smallest hole is 50 and biggest shaft is 48. So still there is a gap. Okay, so still there is a positive gap. So here you can see here a positive symbol. So that we call that gap, this empty thing, we call allowance. Okay, so allowance the positive. So every time if you insert the smallest shaft, so there will be still positive gap. Okay, so positive allowance. So if you have every time positive allowance, we call a clearance fit. Okay, so more looseness there. So every time there is a positive gap, we call clearance fit. So it's easy to assemble, easy to use, easy to replace the parts. Another one is next one is interference fit. Interference fit, we have negative gap. Okay, so every time the shaft has bigger size than the hole. Okay, even though if you insert into the biggest hole the smallest shaft, still you will get the minus size, minus allowance. Okay, so there are no gap. So let's see, the smallest one is this one, 13. Okay, 513, and the biggest one is 519. So let's choose the smallest shaft, 513. But the biggest hole, choose the biggest hole. Biggest hole is 506. Okay, but smallest shaft is bigger than even though 506. Okay, so in order to insert this one, we need a force. Okay, so we need a force. We need a preheat. Okay, so we have to heat it up to insert this one. So heat this one, heating this one, and then cooling this one, cool this one, and then make a force, and then you know just leave it. So then that will touch. Okay, that will insert it with the force. Okay, so because allowance is negative, so we call this interference fit. So it is the sizes of this outer size of the outer surface of the shaft always touching into the inside of this hole. Okay, so we call this one interference fit. We use this one for power transferring. Okay, in the inside of the gear, you know, to join, to assemble gear, the gear part with shafts. Okay, for power transmission. And another type is transition fit. Okay, so transition fit. So in this example, in this mating type, we have positive allowance and negative allowance also. Some of the values might insert it with like a clearance fit. Some of them will be like interference fit. So that's why we call transition fit. So here, if you see, the smallest is 503, but here the biggest is 506. So there is a still there is a gap. Okay, so like say, okay, 12.503, 4, 5, 7, 8, and 9. and here 5 or 6. The smallest is okay 500, 1 2 3 4 5 6. So from 3 to, so here is 6. From 3 to 6 can enter, right? So here can enter easily, and from 6, okay, from the 7, okay, from the 6 to the 9, it will be like a interfere the inside of this hole. So that is a that will be, it's not easy. So we have to use a heating and cooling for these sizes. But from 3 to 6 was inside of this value, so it's easy to insert it. So that would be a clear positive allowance in this case. And in this region, that is a negative allowance. Okay, so we use a heating for this one. So that's why we have both types of the allowances. We call this one transition fit. Okay, so transition fit. Okay, so the limit dimensions are a method of directly specifying tolerance by providing dimensions for upper and lower limits of the feature's size. Like we can do like this calculations. Okay, so we are choosing a smallest possible, okay, so the smallest hole, and we will calculating the smallest difference of smallest hole and biggest shaft, and smallest shaft and bigger hole. Okay, so difference of this. So here we can see this the shaft is given like this, and hole is given here in this part, and we are calculating the tolerances of the shaft, like biggest possible. From the biggest one, this one, we are subtracting the smallest one. So 31.7 minus 31.67, so we will get the difference of this value. Okay, so we call this one IT grade also. Okay, so IT grade. And the hole tolerance, so from the biggest one we're subtracting this one, the smallest one, 31.78 minus 31.75, we got again this kind of value. So that's the hole tolerance. Okay, so there is a two types of the fit: loosest fit and tightest fit. So we are choosing a largest hole. Largest hole is 78, right? So this one. For this one, we're inserting the smallest shaft. Okay, smallest shaft. Smallest shaft is this one, 67. And so in this case, we will have more bigger allowance. Okay, so more bigger allowance. So here, that calls maximum clearance. Maximum clearance. So from the largest hole, we are subtracting the smallest shaft, and we'll get maximum clearance value this. Okay, so that's the loosest fit. Okay, so that's the bigger allowance inside of this. Okay, so the smallest shaft in largest hole. That's that will be more room, more bigger area inside. Okay, so distance inside. And in the allowance, so we call allowance in the difference between the smallest hole and largest shaft. Okay, so smallest hole is smallest hole is here 75. Okay, 3175 minus bigger, okay, larger shaft. Larger shaft is 70 here. You see, so 70. So 75 minus 70 is 0.050 millimeters. So that we call allowance. Okay, so allowance. Okay, so this is the tightest fit that is possible with smallest distance. That is what we call tightest fit. And there is a non-interchangeable fit also possible. That is very specific fit. So how to do this? We are producing a part. We are producing a part with given tolerance. Okay, whole tolerance. So the part, when we say the whole part, so there is a many other sides of the part, but with part of this came with whole. Okay, we're producing 1,000 of this, 1,000 parts, but the shaft part is very specific. So we are not producing many times. So we are making a part with 14 or something, okay, 14 or 15 diameter, and we are putting inside here. If not cannot insert, so then we are making a kind of, some operation, manufacturing operation, like polishing, okay, and then inserting. So if not, again polish, and then whenever if you insert this one, so that part will be inserted. So that part will be specific for this, only for this hole. Okay, so not other holes. So then for the another part, we are doing same operation. So then this part will be only for this hole. This part is for only manufactured for this hole. Okay, so in this case we are not having tolerance here. We have to write it here. Okay, so machine for this part number, fit at assembly. So that calls non-interchangeable fit. So that is very expensive process. So every time you have to polish and then insert it. Okay, so that's very expensive process. So that is unique parts, unique products can have that kind of operation. So or the manufacturing rate is very small, like 1 or 2 parts in a day, or in one operation. Okay, so that kind of manufacturings can use that kind of non-interchangeable fit. That is very expensive thing. Okay, selective assembly. The cost of manufacturing parts with close fit is maybe very high. So as I told you, if you do like this specific, okay, so non-interchangeable fit, so your manufacturing will be expensive. Like Rolex watch, it's very expensive, $10,000, $15,000. Like if you do in mass production, it like in Chinese production, that will be $10, less than $10. Okay, so how they did it, how they reduce the price of the cost of the production or cost of the good. There is a 2 example is given. So this is a first example. This one is first example, example 1, and in the bottom there is another second example. Okay. In first example, we are producing a parts with hole, and we are putting in one place. Okay. And if you see, the holes are different. Okay, so the bigger one and smaller one, smallest one, and biggest one, biggest. And here the shaft part. Okay, so even the smallest one, smallest, and the biggest one, and middle one also is somewhere. Okay, so middle one. So to fit them, okay, so we are taking the smallest one, right? So and then we are matching it. So if it's okay, it's okay. If not, we are putting it in own place, and then taking another one and checking it again. If it's okay, not okay, putting again the place, and then taking it another one. So finally we will get what fits, what kind of the fitting one. Okay, so it will take the time. Okay, take a time. Time means money. Okay, so time consuming. So what we do is we are making a classification. Okay, so we are making a 3 boxes. We are making 3 boxes, and then we are putting holes in the box 1, the smallest one. In the box 2, we are putting middle one. In the box 3, we are putting a biggest one. Okay, so near to this one, we are putting the shaft with smaller diameter, and in nearby to the second box, we are putting another second box for the shafts. Okay, so middle shafts, and then nearby to the third one for holes, another box, the middle, okay, the largest shaft one. And then when you choose this one from this box, it's easier to find a mating part. Okay, so easy to find because it's reduced numbers, and it's easier. Okay, so to find it. That's the meaning of the tolerance. Okay, so you're reducing the time for finding it, and then for the producing and measuring it. Okay, so you are having only the measurements for large parts. You are having in nearby these boxes, you will have the machines. Okay, so specific machines for these sizes, specific tools for measuring, and okay, so for transportation also. And for small parts, you have smaller tools to manufacture, to measure, and to carry out. Okay, so to transportation. Okay, and also skills of the manufacturer, skills of engineers might different. Okay, so different skills might be required. Okay, so if you make a classification, you can reduce manufacturing cost. Okay, so to avoid expense as a manual or computer controlled selective assembly is often used. In selective assembly, all parts are inspected and classified into several grades according to actual sizes. Okay, so we'll have grades. Okay, so boxes like, okay, box 1 up to 3, but that is just for introduction. In the tolerance system, we have more boxes. Okay, more classification items. So we'll see in next pages. Okay, so there is a size definitions. So we have before doing anything, we are planning, right? We are doing a planning, and we are doing a modeling. Okay, so in the computer, in the CAD software. So we call this one nominal size. Okay, so in the CAD, you are writing like, okay, so diameter is 50, so 50, just 50. That is very, that is ideal one. We never reach this one, but we plan to make like this. Okay, so that is nominal, we call nominal size. Okay, so it's used for general identification. It's usually expressed in decimals. Okay, and basic size is, okay, so if you have tolerance 50 plus and minus 1 millimeter or 0.1, so this one is basic size. That's a basic size. 50 is basic size. Okay, so is a size from which limits of size are determined by applying allowances and tolerances. So we are adding and we are subtracting from this value. So this is a basic size. Actual size, okay, and then we're producing it, right? So the part is produced. Okay, so and we are measuring it. Okay, so so we are producing the part, and then we are measuring it. We are measuring after the production. Some of the parts may be different than 50.1, and some of them might be less than this. Or okay, so we are measuring it by measuring device. Okay, so a lot of devices possible, and so that calls actual size. Okay, so it's measured size of the finished part, manufactured part. Allowance is a minimum clearance space or maximum interference. Okay, so the allowance we already seen in previous slides. So this one. Okay, so this one. Okay, so the minimum, the distance of largest shaft and smallest hole, and smallest shaft and largest hole. Those are allowance. Okay, so if you see more closer to the mating parts, so you will see this kind of distances. So this is a basic size. Okay, so distance. Okay, so this is a hole, and that's a shaft. This is a shaft. Okay, shaft can be the smaller one, so it has a minimum diameter and but the maximum possible diameter. And hole also has the minimum size and maximum size. So okay, so the difference is this one, and difference between these two, and okay, so give you the IT grade, international tolerance grade. Okay, so in here the difference of between this the smallest, okay, maximum and minimum size of the hole, and also that is taken into account this, the basic size is taken like this, and difference of the smallest possible shaft and the basic size is given like international tolerance grade for IT grade. We call IT grade shortly for the shaft. That is IT grade for hole. And the distance between the smallest hole up to the basic size give you a lower deviation, and the biggest one is upper deviation. But in here the smallest shaft give you a lower deviation, and the biggest shaft give you the upper deviation. Here the opposite. Smallest give you the lower, but here smallest give you a lower deviation here, and smallest give you a lower deviation, and the biggest hole give you the upper deviation. Biggest shaft give you the upper deviation here. Okay, so here the basic size is ideal one, and minimum shaft, maximum shaft. So the maximum between the basic size give you the upper deviation, minimum, okay, so maximum, okay, minimum one give you the lower deviation. Okay, so here the hole and the smallest hole give you the distance in between the basic size give you the smallest give you the lower deviation, and biggest one is give you the upper deviation. Okay, so here the basic size is ideal one, so you never reach this one. Minimum shaft size, maximum shaft size, minimum hole size, maximum hole size. So we are we are making a grids in between these gaps. Okay, so that's a terminology. And distance. Okay, so there is two things, right? So first thing is international tolerance grid, we call IT grid. You need to understand. And second thing, fundamental deviation. Okay, so fundamental deviation. So fundamental deviation is the distance in between basic size and the distance, the smallest hole and the basic size. Okay, smallest hole and basic size, distance in between this here. And here also the biggest shaft and basic size. Okay, so this one, biggest shaft and basic size, smallest hole and basic size. So that's the fundamental deviation distance. And IT grid is distances in between the shafts. Okay, so between the shafts itself, or between the holes itself. So big from the biggest one and biggest hole and smallest hole, the distance in between. Okay, and between this maximum shaft and minimum shaft. Okay, so that's IT grid. Okay, maximum minus minimum its own sizes. Okay, so that will give you an IT grid. Fundamental deviation is given like basic size and difference of the shaft or hole. Okay, so smallest hole and given basic size, and the biggest shaft and basic size. Okay, so that is fundamental deviation.